Hi guys, welcome to the next lesson for physics. So today we're going to be using what's called distance time graphs. So you're going to describe the journey that an object takes by using a distance time graph. We're going to use the equation for speed that we looked at last lesson and calculate the average speed of a journey by using a distance time graph as well. We're also going to try and differentiate between average speeds and instantaneous speeds as well, because they are two different features on a distance time graph, but we'll go into that once we actually start the lesson. And I want you to be able to draw distance time graphs from given data as well. As per usual, please make sure your phone's turned off or it's in a different room. Don't have any other tabs open on your computer. Make sure you answer all the questions in your booklet and pause the video when I ask you to do, or when you need to give yourselves a bit more time. You can always rewind the lesson and listen again if you're not sure about something, but remember, do not give up. So please do the do now activity. Just to recap what we did last lesson, pause the lesson here, please. Okay, and now we will go through the answers. So the majority of these questions require you to use the equation from last lesson, which was obviously speed equals distance divided by time. Again, what we've done on these questions here is look at the units. All right, we're making sure that we're consistent with our units and that we're not having to convert where we don't need to. Okay, so number one, what is average? So the term average, or maths you'll use the word mean. It's all about average speed is about looking at the whole journey of a particular object. So obviously if you're in a car, you'll travel faster at certain points and slower at other points. So average is basically what is all of them put together and what's the general answer. So for number two, calculate the speed of a line that runs 100 meters in 4 seconds. So calculating speed equals distance divided by time. So my distance is 100 meters divided by a time of 4 seconds. So my answer is 25. Please don't forget your units. It's 25 meters per second because it's a divide. Calculate the speed of a car that travels 54 kilometers in 0.9 hours. So here you've got kilometers and hours rather than meters and seconds. And we normally like to work in meters and seconds for physics. However, here we can just put the speed of the car in a different set of units. It just depends on what your unit of distance is and what your unit of time is. So we still use the same equation, speed equals distance divided by time. So my distance is 54 kilometers, my time is 0.9 hours, which gives me an answer of 60 kilometers per hour rather than meters per second, because look at the units that we were given in the question. Finally, number four, plane travels at a speed of 695 kilometers per hour. How far will it travel in 12 hours? So we need to rearrange the equation because we've been given the speed. Okay, it says kilometers per hour, so that's a unit of speed. It's asking us the distance, how far it will travel in 12 hours. So I don't need to convert anything. I don't need to swap hours for seconds because my speed's already in kilometers per hour. So I need to make sure that my time unit is the same there, which it is of 12 hours. So rearrange the equation. If speed equals distance divided by time, distance equals speed times by time. So 695 times by 12 gives you 695 kilometers because they were the distance units in the speed. Please make sure that you've marked them off and corrected if you're needed. Okay then, distance time graphs, okay? Basically allows us to have a look at a journey by an object. More often than not, it'll be a person running, a car or a cyclist, some things like that, okay? And they look something like this. So we've been given a graph, and so first of all, first thing you do with any graph is you always look at the axes. So here, I'm looking at the fact that I've got a time along the x-axis, so it's showing me time changing, and then I've also got distance on the y-axis. Okay, you always go to your axes first because you want to know what the graph's actually telling you, and you get different types of graphs like this. There's other graphs that aren't just distance and time. All right, so on this particular one, we've got time and distance, so it definitely is a distance time graph. Please note how we've got the units in brackets there as well. So time is measured in seconds, distance is measured in meters. So here on this graph then you can see we've got a couple of plots, we've got lines going up and then down, things like that. Okay, if we look at the different sections, we'll just go through what they actually mean. So as time goes along, if we go along this x-axis, which is what it's telling us, so as time goes along, the line starts to increase. And so what it's telling us is as time increases or time moves forward, our distance that we travel also increases. So if you time yourself walking somewhere, if you start at 0, set your stop clock, as you walk, you start covering distance. And so we'd be able to plot this line for you. Now, there's certain things we need to pick out on this particular graph. So I'm going to look at the linear slope to begin with, and that's this bit here, okay? So this is a linear slope, and the word linear means straight, basically. So I've got a straight line here, okay? So it's a straight line. Now, if you've got a straight line or straight slope on a distance time graph, it means that you're traveling at a constant speed, okay? So that is a constant speed, and apologies for the writing because I'm struggling to draw with my mouse here. Constant. So constant speed. You know what? I'm just going to, you can listen. That's constant speed. Basically means you're covering the same amount of distance per second. So if you were doing a speed of 5 meters per second, you would be covering 5 meters every second. So after 1 second, you'd have done 5 meters. After 2 seconds, you'd have done 10 meters. Okay. So that's what that tells us there. And then if you have a look at the other lines, you'll see that they've all got different features associated with themselves. Okay. So if we have a look at the curved slope, okay, which is here, so curved is in this bit here, all right, all the way up to there as well. If you've got a curved line, it means that your object isn't traveling at a constant speed. It's still covering distance because it's still moving higher up. However, if it's curved, it means that your object's accelerating or decelerating, slowing down in speed. So on this curved slope, what's actually happening is we are accelerating. So we're getting faster, which means that we're covering more distance in a small amount of time. Okay. If it was to curve the other way, you'd be slowing down. And so we'll look at that later on. But here we've got that upwards curve. And so you are actually accelerating. Your distance and time are no longer proportional to each other. If we look at some of the other lines then, so here I've got an example, I'll do it in a different colour for you. So I've got a flat line there, all right, and I've got a flat line here. If you've got a flat line, just have a look at what it's doing with the axes. Your flat line, time is still going forward. So here, this flat line started at about 3 seconds. So 3 seconds, 4 seconds, and then 5 seconds. So time was still moving forward, but notice how the line isn't going upwards. So you're not increasing in any distance. Now, the only way for you not to be increasing in any distance is if you've done something. And so a flat line means that you have stopped. You are stationary. Okay, so you are not increasing in any distance. So a flat line on a distance time graph means that you have stopped. Okay. So on this particular example, there's 2 occasions where he's stopped. And then if we keep on going forward and we have a look over here, if we have a look at this straight line there, this straight slope, notice how, okay, remember what we said earlier about a straight slope, constant speed at the beginning there, because it's a straight linear slope going upwards. This one isn't as steep as the first one. So it's still a straight slope, so it's got to be some form of constant speed, except because it's not as steep, it just means it's a smaller constant speed compared to that first one we looked at to begin with. And then your final one that we need to look at is this bit here, there. We've got our slope coming back downwards, okay? Now, on this particular example, depending on the terminology we use, theoretically what we should have used here was displacement if we're going to look at this downward slope. It's a straight line again, right? Straight linear slope going downwards, which will mean that it's at a constant speed. But because it's going down, we'll be looking at displacement, and it'd be called going backwards. Okay, distance is a scalar quantity, and so you can only ever move forward with scalar quantities. Okay, so if you imagine you're walking forward and backwards, if you walk 1 meter forward then 1 meter backwards, you've actually done 2 meters. displacement, you'd have done 0, but we'll look at that in a different lesson. So, if you see the word velocity, it's just a synonym of speed. Velocity is speed in a given direction, because it's an example of a vector quantity. So you could say that this is constant velocity at the beginning, that first slope, and this one up here is another constant velocity. So if we start to see the word velocity creeping in as well, it just means speed. Okay, so let's have a look at these key features then. So distance time graph again, just look at your axes. Yep, time on the x-axis in seconds, distance on the y-axis in meters. So if you've got a flat line, it means that it's at rest, stationary, not moving. Again, distance time, if I've got a linear or a straight slope, it means constant speed, same speed. You're not increasing in speed or decreasing in speed. And if you've got a curve on a distance time graph, it means you're accelerating. And don't forget, you could have a curve that does this. And so another curve could go like that, in which case it'd be decelerating. So I've got to be careful. They'll try and trick you, make it a bit more difficult on those points, okay? So just pause the lesson here and just make sure that you can identify each one there. It should be pretty easy. So on here, A is at rest, B is constant speed, C is accelerating. All right, that should have been fairly simple for you. All right, make sure you just corrected your answers and we'll carry on. Okay, on this one then, this looks like a much more detailed version of what we looked at. Again, you see some of those common features. It's a graph, so what do we do with a graph? We go straight to the axes. It's a time graph along the bottom and distance in meters up the side. So it is a distance time graph, okay? So let's have a look at describing this journey. Now, what you can do is we can split this into different sections, because we could look at that, we've got two flat lines, straight, great, we know that that means it stopped. We've got two linear slopes, or three linear slopes, so two of them going upwards, which means we know it's constant speed, and we've got the one coming down again as well. Now, I can split it into different sections. I'm going to label those different sections, okay? So I've got A, B, C, D. I've basically done that, but when there's been a change in motion ultimately, because B there was stop moving, C increased, got to normal speed again, D stopped moving and then started to go backwards. Okay. And so what that does is it helps us read off on the axes here, because at some point we're going to have to use the equation from last lesson along with these numbers. Okay. So make sure that you're using a ruler to read down, so that you're intersecting the correct numbers. And again, we're going to be reading across at different parts as well. So for example, in part A, if I want to look at part A, right? Because remember, we can either look at the whole journey or we can look at different sections of the journey. So in section A, how long is it actually, or what is the distance covered in section A? Well, let's have a look. In section A, where do we start? Well, we started down here at 0. All right, that's where we started. Where did we end up in section A? We ended up at 200 meters there, you see. And so section A just covers from 0 to 200. So in that case, it was 200 meters covered in that section A. How long did that take him? Well, times our x-axis. So that's where section A begins with. Here's where section A ends. So you've got from 0 to 1, which would give us 1 minute. So he's done 200 meters in 1 minute, like you can see on the answer there. On section B, what's the distance he's done? Well, his starting distance is here at 200. His end distance in section B is there, still at 200. So he's actually done 0 meters. So he's actually stopped. And we know that because we know that a flat line on this graph means that stationary. In terms of how long that took him, well, let's go down here. What was the time when he started to stop? So let's read down, start of section B. It was 1 minute. What did section B end? At 4 minutes. So how long has he stopped for? Well, he's gone from 1 to 4, so it must be 3. And then we do that for each bit. Section C starts at 200 meters there. Where does it end? 800. So you've gone from 200 to 800. How much have you done? 600 meters. How long did it take? You've gone from 4 to 6. So going from 4 to 6 will be 2 minutes. And you can do that for each individual section. So part D, flat line, so there's no distance, but it's gone from 6 to 9, so that's 3 minutes. Section E, he's gone from 800 all the way up there down to 0. So he's done 800 metres. How long did it take him? Well, he started at 9, ended at 13, so you've gone from 9 to 13, so 4 minutes. Okay, this is important because the harder questions are going to ask you to calculate speeds at different parts of the journey. So it might be the whole journey, it might ask for an average speed of the journey, or it'll ask for specific sections of the journey. Okay, so make sure that your graph looks like that. So let's have a look at actually calculating speed then. Okay, so if we go back to the equation for speed, speed equals distance divided by time. Average speed would be equal to the total distance covered divided by the total time it takes. So that's where you've got to read the question carefully. Is it asking you for the average speed, which is for the entire journey, or is it asking you for a specific section? Okay, obviously, if you've got a flat line, you have stopped, then your speed is 0 meters per second or meters per minute or whatever the units involved are. Okay, so let's have a look at putting that into action then. So part A, right, let's calculate, and we need to be meters per second because we like meters per second in physics, to work out the speed at part A. So I want to work out the speed that he's travelling at the first part of his journey. So he's done 200 meters in that first bit. So I've got my distance. Don't forget the equation. Speed equals distance divided by time. And it took him 1 minute. Now, if you look at your units up here, it's in meters per second, not meters per minute. So we need to convert our time into seconds. So 1 minute is equal to 60 seconds. Okay, so I've now got my time in seconds. So he's done 200 meters in 60 seconds. How long has that taken? Well, put it into your equation. Speed equals distance divided by time. 200 divided by 60 equals 3.3 meters per second. And again, look at those units. Okay, and so that is one example that we've done there. Can you now just pause the lesson just very quickly and have a go at calculating the speed at part C? And if we look to the answer, we already said that B was 0 meters per second because it's covered 0 meters, right? That's why I didn't want you to do that one because we've already discussed it. Part C, well, we identified that it covered 600 meters and it took him 2 minutes. So 2 minutes, if 1 minute is 60 seconds, then 2 minutes must be 120 seconds, okay? So 600 divided by 120 equals 5 meters per second for part C. So we can see there that he's traveling much quicker at part C than he was at A. A was 3.3, C is 5. Okay. Another way you can visually see that is by the steepness of the slope. The steeper the slope, the faster your object is going. Okay. And then here, if we look at section E, because D is flat line, section E, they cover 800 meters in 3 minutes. So 3 minutes times by 60. Sorry, it's not 3 minutes, it's 4 minutes. 4 minutes times by 60 is 240 seconds. So speed equals distance divided by time, which is 800 meters divided by 240, which is 3.3 meters per second. So even though the line is a lot bigger in section E, he's actually traveling at the same speed as he was in A because they both came out at 3.3. Now, again, we've got this idea surrounding key terms, because that's his speed that we just worked out. Whereas if we were to look at velocity, velocity depends on direction. Okay, basically means you can have a negative value of velocity. So in this example, or in a simple example, if you're going backwards, we can give that distance or displacement a negative value. And so if we calculated the speed at section E with a negative distance, you'd end up with a negative 3.3. And it'd just mean, all that negative would mean is that the car is moving in the opposite direction to what it was before. Okay. Right, just pause the video for a minute, please. I'd want you to calculate the total distance that is travelled by the object, and then I'd like you to calculate the total time that it took. Okay then, so total distance, well, we had 200 at the beginning, section A, plus 0 at section B, because it stopped, 600 at C, plus 0 at D, plus 800 at E, gives you a total of 1600 metres. The total time then it took, and it's really easy to look at total time, just look at where your line ends. So you can add up the individual times, which would be 1 in A, 3 in B, 2 in C, 3 at D, 4 at E. They'll add up to when the line ends, which is actually at 13 minutes. But we're physicists. We want that in seconds. So 13 minutes, we know that there's 1 minute, 60 seconds in 1 minute. So 13 times 60 is 780 seconds. So here, what we're doing here is, because we're looking at the total distance and the total time, is we're going to work out, right, what was the average speed for the entire journey. That's what we're looking at. And in order to calculate average speed, we need the total distance and the total time it took. So whereas we've worked out individual speeds for different sections, they're going to be different to the actual average. So my total distance is 1600 divided by my total time, which is 780, which gives me an average speed of 2.05 meters per second. So notice how the average is less than the two values that we calculated for the different sections. You know, we calculated 5 and 3.3s, because it's also taking into account the fact that at different stages the car wasn't moving, it had 0 speed. So if you average all of them together, it's going to lower it down slightly. Right, I would like you to now complete the using distance time graphs worksheet. Okay, remembering key things that we've discussed so far in terms of what features on a distance time graph actually represent and how to use the equation. Okay, so pause the video now and attempt the worksheet. Okay then, if we're ready for some answers, please get yourself ready. So number 1, correct description match to the graph. So in graph A, Lizzie runs to the end of the road, realised she left the phone at home and heads back home to collect it. B, lion stalks by moving slowly and then stopping occasionally. C, mouse runs fast to get away from the cat. Okay, so it's all about application at this point. Number 2, you're identifying your different times. B, speed equals distance divided by time. You're then looking at individual speed, so distance covered in that section was 30 metres because it starts at 30, ends at 60, so that's 30. How long did it take that? Well, it started at 60 seconds, ended at 120, so it took 60 seconds. So speed equals distance over time, 30 over 60, 0.5 metres per second. D, you've got distance to 60, time of 40, so 60 divided by 40 is 1.5 metres per second. E, you've got your two time answers there. And then F, you've got your final speed as 0.67 metres per second. So very quickly, a quick fire round. Which slope represents the fastest speed? You've got 5 seconds. The correct answer is obviously A, the green line. Okay. Next question. In which graph is the object not moving? 5 seconds. It is, of course, graph B, because a flat line means not moving. Which object is travelling at a constant speed? It is, of course, graph C, because we've got that linear slope, so which means we're covering the same amount of distance per unit time. What's the correct equation for calculating speed, please? 5 seconds. It is, of course, C, speed equals distance divided by time. Which is travelling fastest? I'll give you a bit longer this time, so you don't have to calculate. It is letter B. So on this one, you do distance divided by time. So A would be 40 over 10, which is 4. B would be 40 over 4, which is 10 metres per second. And then you've got a snail that's moving 40 and 400 seconds. Ultimately there, because it's the same distance, whichever one does it in the quickest time, it's going to be travelling fastest. Right, guys, can you please complete your KPI task? Pause the lesson here, and then we will have a look afterwards. Right then, guys, let's prepare ourselves for answering. Just use your answers that are given to you in the folder. And then you have got a final activity there if you want to pause it. And if you've got the materials at home, have fun making it. Bye guys, thanks a lot. I'll see you again next week.